Hello, everyone. Happy New Year. I hope you had a great winter break. On behalf of the Science Institute, we would like to welcome you to the new academic quarter. I am Nicoletta Cristia, and together with Dr. David Beck, we are hosting the Data Science Seminar. Our colleague, Louisa Kaler, you can't see her, but she is here from the Science Institute, is also helping with the seminar logistics. As part of the University of Washington, we acknowledge the Coast Salish peoples of this land, the land which touches the shared waters of all tribes and bands within the Suquamish, Tulalip, and Muckleshoot nations. Joining us today is our first speaker, Dr. Steve Mussmann. Steve is a postdoctoral fellow in the Paul Allen School of Computer Science and Engineering at the University of Washington, working on machine learning methods that reduce the required amount of data. He received a PhD in 2021 from Stanford University in computer science and a bachelor's degree in 2015 from Purdue University in math, statistics, and computer science. Today, Steve will talk about reducing data and computational requirements in machine learning with data selection techniques. Please use the Q&A feature of Zoom to ask any questions you may have. And Steve will address them at the end of his talk. And with that, Steve, please take it away.
All right, thank you. Thank you for the introduction and thank you for the opportunity to speak here. So I'm going to be talking about my research that I've done over as my PhD as well as more recently in my postdoc. So generally my research focuses on machine learning, in particular with emphasis on data selection techniques. So let's jump in. So machine learning in its simplest form, perhaps you can think about it as data, some data which we perform computation on, some sort of training, to yield a predictor with some associated performance. So as an example, one data set that I'll be using throughout the talk is CFAR10, which is a standard image classification data set, where we have images of animals and vehicles, such as that are labeled with categories, 10 categories, such as bird, car, and horse. Then the computation part is optimizing a loss, maybe something like gradient descent over some model parameters. And then in the end, we get a neural net with trained weights with some associated test error rate, perhaps 6.3% in this case. So looking at this sort of pipeline, if you want to get a predictor that you can deploy somewhere and make predictions, an issue is that there are costs associated with machine learning, in particular, data costs and computation costs. So let's first motivate the data costs. So data can be expensive. In some areas like medical image classification, for instance, classifying X-rays as with a diagnosis, require medical doctors as the label annotators. Data collection can also sometimes require real-world experimentation, such as running biochemical reactions, which are expensive, can be expensive as well. To give you a sense of the scope, one particular startup that labels text and images and videos called Scale AI has an annual revenue of over $100 million. So this is relatively big business in terms of the cost of data. So to alleviate this, one natural approach is to simply decrease the amount of data required in this learning pipeline, and this will reduce costs. Computation can also be expensive. So we usually think of this as the cheap part of machine learning, but especially with the recent interest in large pre-trained models, such as large language models, CLIP or ImageN, there is a large need for computation. So for instance, CLIP was trained on 400 million image text pairs and required weeks of computation on hundreds of GPUs. And to give you a sense of the monetary scale of this, Stable Diffusion required $600,000 just for the computation cost to train. So there's many approaches to decrease the computational cost for machine learning pipelines, but one way to do it is by decreasing the data. Usually if we're doing gradient descent or something, the optimization will take time proportional to the size of the data set. So if we can filter out the not so important data points and only focus on the important data points, we can decrease the computational resources. So that's sort of the area of my research, is to mitigate the data collection and computation costs, try to collect and train only on the important data points. So here's a little schematic of machine learning data and a classifier. Kind of the 2D position represents the features, and the symbol and color represent the class, either negative or positive. And this black line is a linear classifier. So there's several intuitions for why we might expect to be able to prune data sets and only focus on, and some data points are more important than others. So for example, there's redundancy. Sometimes in a data set, there will be many data points that are very similar to each other, and we only need a few of them. We don't need the full number. Some data points are somehow easier than other data points, and it's not necessary to include these in the data set because they'll be classified as correct quickly anyways. There also are rare classes or phenomenon shown here at the bottom that are often more important to include in a data set. Things such as in self-driving cars, key events such as objects on the road are much more important to collect and label rather than highway driving video. So I want to instantiate this with one specific model to sort of flesh this out. So imagine you have an input space of x's between 0 and 1, and a w star, which is some parameter between 0 and 1 as well. And the label of a point is positive if x is greater than w star, so if it's to the right of w star, and y is negative if x is to the left, is less than w star, or to the left of on this diagram. So random sampling looks like the following. We have a lot of unlabeled data points. We send them all for annotation, and then we train a model to get maybe w hat. And this is sort of a standard approach that we'll be comparing to when we talk about the advantages and disadvantages of active learning and data pruning. Active learning, on the other hand, is where we are actively selecting which data points to label. Hopefully, we're selecting the most important data points. So in this example, we can actually do a lot better than random sampling. We can do something like binary search, where we first select a point in the middle, label it. If it's negative, we know that w star lies to the right. Select a point in the middle, label it. Now we know that the w star lies in between these 2 points. And repeating the strategy of labeling points in the middle, we can get to much smaller error bounds on w star with fewer labels. Here, we required something like 8 labels rather than the 30 in the previous for random sampling. So this will be the main topic of the talk. I also just want to briefly mention machine teaching, which will come up later. So for machine teaching, we know w star, and we're simply trying to select data points to convey to a learner and convince them so that they arrive at the right conclusion. And for thresholds, this is very simple. You just require 2 data points arbitrarily close to w star, and this will give arbitrarily low error. So these are kind of 3 settings we can look at. Random sampling, where we randomly sample a set of points and receive the labels, something like the default. Active learning, where we adaptively select points to label. And the machine teaching, where given full knowledge of the labels, select a subset to train on. All right, that concludes the introduction. So I've divided this talk into 2 main parts. First, active learning. I'll cover 4 projects I've done on understanding uncertainty sampling, one particular active learning algorithm. And later I'll transition to data pruning and look at some machine teaching approaches and some other approaches we've developed. And finally, if I have time at the end, I'll go through future work. So let's jump into uncertainty sampling. So in the active learning literature, there's roughly two branches of literature. The more empirical branch, which designs effective methods and is empirically motivated, though theoretical guarantees and the theoretical understanding are less important. There's also a theoretical branch, which has a rich theory and theoretical guarantees, but not as practical algorithms. Uncertainty sampling is the most popular active learning algorithm in this empirical branch, likely due to it's very simple to implement. It has strong performance, even compared to recent active learning methods. However, on the downside, it does have little theory. So there's not a great understanding of when and why the uncertainty sampling works. So this will be the goal of one line of work. The first part of the talk is providing more theoretical background for uncertainty sampling. Well, what is uncertainty sampling? So if we have in standard data collection, we have unlabeled points, we label the data, and then we fit a model. And this is great, but we might be able to do better. Uncertainty sampling, a nearly 30 years old algorithm, proceeds in the following way. First, we label a seed set, that is a randomly selected small set, fit a model. So this is like a max margin classifier to separate the existing labeled positives from the existing labeled negatives. We label a most uncertain point, that is the point closest to the decision boundary, in some sense, what the model is most unclear about. We fit the model again with our existing labeled data points and repeat this process iteratively. Label the most uncertain, fit a model. Label, fit, until we have the same decision boundary, but we use much less data. So all these data points, we didn't have to pay an annotator to annotate. So uncertainty sampling comes with some challenges as well as gains. And I'm going to be talking about four aspects. First, I'd like to talk about the non-consistency of uncertainty sampling. So one thing about active learning is it changes the training data distribution. Instead of just uniformly selecting points from the domain, instead we are selectively choosing points. And this means that what the learner sees, the learning algorithm sees, is a different data distribution. So thus, the active learning predictor doesn't necessarily converge to the same predictor as random sampling. And we call this non-consistency. So like in the stats literature, we say an estimator is consistent if it sort of converges to the right thing. And active learning, and uncertainty sampling in particular, is not necessarily guaranteed to converge to the right thing. So here's an example. So again, we have a set of unlabeled points. We label a seed set, fit a model, label, fit, etc. And it looks like we've attained the same feat, that we only have labeled a few of the data points, and we have the points near the decision boundary labeled. But if we were to deploy this system, we would quickly see that we actually missed an entire cluster in the upper left. And actually, in fact, the sort of right answer, the best decision boundary, is a horizontal line. So where uncertainty sampling converged to, this line, is different from the right answer. So this is what we mean by non-consistency. So we're going to be examining convex loss models like regularized logistic regression. And we'll define the optimal parameters, sort of the right answer, so to speak, as the parameters that minimize the population convex loss out, sort of the loss averaged over the whole population of data points. So training on randomly sampled data converges to theta star under pretty mild conditions. What about uncertainty sampled data? So this non-consistency has been observed, both that the non-consistency can hurt performance, like we saw in the previous example, but perhaps more surprisingly, the non-consistency in active learning can actually improve performance. So algorithms, generally like uncertainty sampling, can actually achieve better performance than theta star. So we'll explore these two phenomenon and explain them, so to speak. So I'll fast forward to the result that under some conditions, uncertainty sampling implicitly locally optimizes the 0-1 loss. That is the misclassification error. So this is perhaps surprising. So uncertainty sampling at every stage is labeling a point and minimizing the convex loss, labeling a point, minimizing the convex. What it's implicitly doing, sort of mathematically, is optimizing the 0-1 loss locally. And this local optimization, you can think of it as similar to stochastic gradient descent. So if we define Z as the 0-1 loss or misclassification error for parameter theta, then define error star as Z of theta star. So since random sampling converges to theta star, this will be the error star will be the asymptotic performance or error of random sampling. So a question we might ask related to the previous slide is the asymptotic performance of uncertainty sampling better or worse than error star? So this gets down to the difference between optimizing the 0-1 loss Z versus optimizing the convex loss L. So in this simplified cartoon, we see the parameter space is just a 1D line. L is some convex function on this domain with a unique local minima, which we call theta star. Now, if we want to evaluate how well theta star is doing on test data, we get an estimate by computing error star Z of theta star, which is this level, the Z evaluated at theta star. And now maybe we can see the issue with uncertainty sampling, that if it's implicitly optimizing this Z function, it can get stuck in local minima. So like sometimes uncertainty sampling gets stuck in places like this, but also since we're implicitly optimizing the evaluation metric, we can actually do better than random sampling and get to lower minima of Z than theta star. So I'd like to show this in a computational experiment. So in a synthetic experiment, we have 4 disk clusters with red and blue classes and different mixture coefficients. So what this means is that there's a 30% chance that a point has a red class and is drawn from this left cluster, and say a 10% chance of being drawn from this cluster somewhere in this disk cluster with a blue label. So there will be 4 local minima of Z, corresponding to ignoring each of the 4 clusters. And since it's convex, only 1 local minima of L. And sure enough, if we take this experiment and run it computationally, we can see the pool of points as the red and blue points. And then we run green as 100 uncertainty sampling runs, each with 30 labels. And we see that uncertainty sampling converges to 1 of 4 places corresponding to the local minima of Z. Furthermore, black, or the training on the entire pool, the black line converges to a decision boundary that is drifted a little bit because of this cluster up here. And uncertainty sampling can do both better, such as 10% rather than 18% error, but it can also do a lot worse, such as 40% error or 20 or 30% error. So the takeaways from this section are that the non-consistency is a common issue with active learning algorithms since we're changing the data distribution. Uncertainty sampling implicitly optimizes 0-1 loss, which can yield lower misclassification rate, but it can also get stuck in local minima. And our recommendation is to avoid these local minima, to use a sufficiently large seed set, not just 2 or 3 points, but rather maybe a few hundred points to initialize uncertainty sampling so that we start with a better initialization. Next, I want to talk about dataset dependence gains of uncertainty sampling. So even in cases where uncertainty sampling converts to the same predictor as random sampling, how does does it require fewer labels? So looking at the literature from some older papers, we noticed something that for 3 different data sets and 3 different papers, the same 2 algorithms, red being uncertainty sampling and blue being random sampling, there's pretty different performance. So on the left 2 plots, random sampling does quite a bit worse than uncertainty sampling, while on the rightmost plot, they do about the same. So it would be nice to have a quantitative way of saying, how well things are working. And for this, we'll use the concept of data efficiency. So if we have a random curve, error plotted as a function of the number of labeled data points, and some active learning algorithm, for a given performance level, like say an error in this case, you can compute the number of points it takes random to achieve this performance level, as well as the number of points it takes active to achieve this performance level. Take the ratio, and that's the data efficiency. So in this case, the data efficiency is 3, because to achieve this performance level, active learning requires 3 times fewer data points than random sampling. All right, so going back to these different plots from the literature, the data efficiency varies quite a bit, with more than 5x data efficiency in the first plot, 3x in the middle, and barely more than 1x on the right side. So how do we explain this? Well, maybe it would be easier to look at a simple synthetic example to sort of, there could be a lot of things going on with these data sets. Can we reproduce this phenomenon in a simple setting? So we'll look at class conditional distributions that are Gaussian. So we have, the minuses drawn with mean this, positives drawn with mean this. And then we can, what happens to uncertainty sampling's data efficiency as we vary the separation between the Gaussians. So on the left, we have more noisy data distribution because there's more overlap. On the right, it's less noisy because there's less overlap. But again, what's the quantitative way to measure this amount of noise? And we use the error of the optimal classifier, like the error star in the previous section. So theta star is a minimizer of the logistic loss, the dotted line in the examples below. And error star is the error of theta star, the proportion of positives and negatives on, quote, the wrong side of the dotted line, the ones we misclassify. So for this synthetic example, when there's less separation between the Gaussians and thus higher error star, there's very little data efficiency gains. Active learning and random sampling do about the same. However, when there's more separation between the Gaussians and lower error star, the gains are rather dramatic. And it looks like if we looked at lower performance levels, the gains would be even more dramatic. One thing you'll notice here is that there's quite a big difference between error star. Error star on the left is like 20%, and error star on the right is like 1%. So one thing we might think is maybe when there's the data efficiency is inversely related to the error or error star. So to look at this, we looked at 21 real-world data sets collected from a dataset repository, OpenML, ranging over a wide variety of application areas. And the data efficiency varies widely with, the minimum uncertainty sampling actually performs a bit worse than random sampling, all the way up to almost 9 times data efficiency. And roughly, the inverse error does explain the data efficiency. So if we plot, each point corresponds to a data set where we compute error star and compute 1 over error star on the x-axis, and then we compute the data efficiency on the y-axis. And you can see a rough linear trend with relatively high Pearson correlation and Spearman rank correlation. We also have a theoretical result for this in this case, that for well-specified logistic regression in an asymptotic setting, the data efficiency is indeed goes as 1 over error star. So recall that error star is the asymptotic value of the blue line, sort of random sampling as we get infinite labels. And the data efficiency is computed as this performance drops to the error star. So this is what I mean by in an asymptotic setting. And the proof technique involves a comparison of the Fisher information of random sampling to that of uncertainty sampling. So the takeaways from this section are that the data efficiency of uncertainty sampling is inversely proportional to error star, both empirically and theoretically. Thus, uncertainty sampling and active learning more generally works best when the asymptotic error star is small. And this gives a recommendation to use active learning and specifically uncertainty sampling on less noisy data sets. Next, I want to talk about a specific case study for using the previous insights to get large gains with uncertainty sampling. So we'll examine a data set from natural language processing called the core question pairs data set, where pairs of core questions are labeled as either paraphrase or non-paraphrase. So for example, what are good sports to play and how many sports should I play? Questions that might appear on Quora are not paraphrases because they're related, but they're getting at different things. Whereas what are good sports for fitness and what sports make you healthy, although they're using different words, they're getting at the same thing and would be paraphrases. And models appear pretty good at paraphrase detection. So the state-of-the-art model gets about 90% accuracy, and a simple BERT model where we embed the sentences and put a threshold also gets relatively high accuracy. However, we propose rethinking this data set a bit. So the issue is that standard QQP data set is artificially class balanced. So roughly there's as many pairs that are paraphrases as pairs that are not paraphrases. But this doesn't seem accurate because the vast majority of pairs of questions are unrelated. If I took 2 random questions off of Quora, it's very likely they would be unrelated. So here in this little diagram, you can see that if we look at the question by question matrix, so pairs of questions, then the blue correspond to pairs that are paraphrases and red as pairs that are not paraphrases. Our solution is to create an imputed data set with all pairs of core questions, where a label is paraphrase if that pair appears as a paraphrase in standard QQP. So we've taken all these unrelated gray questions and mapped them to red. And you might be concerned that, well, maybe there's some paraphrase in the gray. But when we looked at the question specifically, we did a systematic study, and this appears to not be the case, that the pairs that do not appear in core question, as in core question pairs data set, are indeed not paraphrased. So what does this all pairs core QQP data set look like? Well, it's very large. Since we're taking pairs, it's 38 billion pairs. It's extremely imbalanced with the vast majority of points are unrelated. Only a small proportion of the 38 billion pairs are paraphrases. And this extreme imbalance implies error star is very small. So the optimal error, error star, is less than the error of the majority classifier, where we just predict negative non-paraphrase everywhere. And we know this is very small since the data set is very imbalanced. So since error star is small, we might be encouraged to try uncertainty sampling and see what kind of gains are available. So our model we call cosine BERT, where we take 2 questions, embed them both with BERT to get 2 vectors, take the cosine similarity between these 2 vectors to get a scalar, and then pass that scalar through 2-parameter logistic regression to get a probability of the pointing of paraphrase. And we can train this end-to-end, both training the BERT embedding as well as the parameters of the 2-parameter logistic regression. And the results are as follows. So if we just use the original balanced QQP data set, which is a little unrealistic because we're using all the paraphrase, we sort of get all the paraphrases for free, the average precision is about 15.4. Random sampling, which will, the vast majority of randomly sampled pairs will be unrelated or non-paraphrases, gets average precision of 2.8, much worse. Static retrieval, which retrieves the most similar pairs according to BERT in the first iteration, gets higher average precision of 25.1. Adaptive retrieval, which also retrieves the most similar pairs, but in 10 adaptive rounds. So we select the points that are most likely to be paraphrases, retrain, select the points that are most likely to be paraphrased with that new model, retrain and repeat this 10 times, we get 32.4. And uncertainty sampling, also when done in 10 adaptive rounds, gets 32.5. So a couple of things to notice: the best non-adaptive method is outperformed by a large margin by the best adaptive method. So adaptivity and active learning is really helping here. But also that adaptive retrieval works about the same as uncertainty sampling, which we found out to be because they're basically selecting the same points. If the model is unsure about points that are likely to be paraphrased. If we look at the data efficiency, uncertainty sampling with 16,000 examples matches the best non-adaptive method with 232,000 examples for 14x data efficiency, which is pretty high, requiring 14 times less data to achieve the same performance. The takeaways from this section are that label imbalance implies a small error star, and thus we might be encouraged to use active learning. And indeed, active learning can yield dramatic results for tasks with extreme label imbalance. And with that, I'd like to finally wrap up the section on uncertainty sampling with looking at the fundamental limitations of active learning. So as motivation, there's been a lot of theoretical work in active learning focusing on the type of dependence of the error on n, the number of labels, exponential versus polynomial dependence, different polynomial powers, etc. And this is important because if a lower asymptotic rate than random sampling is achieved, performance will be arbitrarily better than random sampling for a large enough n. So once I get enough, if the error of random sampling goes as 1 over n, and the error of active learning goes as 1 over n squared, doesn't matter the constants out front, eventually active learning will do better for a large enough n. However, empirically, this doesn't seem to be the case. That active learning seems to perform similar to random sampling in some practical cases, even with large amounts of data. So we look at a specific setting where inputs are uniformly drawn from a d-dimensional unit sphere. So that is, from a sphere. The true parameters have fixed norm. That is, theta star has norm m. Binary label, so y is equal to -1 or 1, and logistic conditional label distribution. So the probability that y equals 1 is close to 0 on one side of the decision boundary, slowly increases until it's close to 1. So standard logistic regression. So jumping ahead to our results, if we define error star as the Bayes error, then up to universal constants, the expected excess with respect to the Bayes error is the following, shown in the following table. So one thing to note is that these lower bounds are for any active learning algorithm, not just uncertainty sampling, any active learning algorithm. And we prove this using an information theory lower bound. In particular, both random sampling and active learning have the same dependence on n for this simple, benign, non-pathological case. So it might be hard to design an algorithm that gets a better dependence on n unless you somehow find a way to exclude this rather non-pathological case of a uniform sphere with logistic regression. Less importantly, we also have upper bounds that roughly match the lower bounds, up to a log d factor for random sampling. And we also have synthetic experiments to illustrate these theoretical results, that the test excess error goes as about 1 over n with the number of samples. And when we fix n and vary the Bayes error, that is error star, the performance of random sampling, the test excess error stays about constant, like our bound predicts. But the test excess error of adaptive sampling, in particular an uncertainty sampling variant, roughly increases linearly with the Bayes error. So takeaways from here is that for practical distribution classes that include this non-pathological case, active learning cannot achieve a better rate than 1 over n. For our specific setting, we show that the ratio of the optimal excess error of random sampling to the optimal excess error of active learning is between 1 over error star and log d over error star. So this inverse to error star does seem to be a somewhat fundamental parameter. Perhaps then it's not possible to always achieve improvements with active learning, but instead the improvement depends on problem-dependent quantities like error star. And that wraps up the section on uncertainty sampling. Next, I would like to switch gears a little bit and talk about data pruning. So the data pruning problem statement is the following. We saw this previous diagram for how a machine learning pipeline looks. Well, data pruning, the problem statement is to find a smaller subset of the data. So this data is a subset of this data, such that when we train with the same learning algorithm, we get a predictor with approximately the same performance. So you can think about this as, the word pruning comes from the idea that we can take out some of the data points without really impacting the performance. What are some applications of data pruning? Well, one is for standard supervision, like I hinted at in the introduction. If you have a lot of data points where everything is known, both X and Y, the input and the label, then training on less data requires less computation. If you could prune out some of the data points, less computation required to optimize. But there's also more nuanced applications as well. So something we call reverse active learning, where the input is unknown, but we can query it, but the label is known. So this, we call it reverse active learning because we call active learning the input is known. So we know the unlabeled data points, but the labels are unknown, but we can query for some cost. So reverse active learning, we know all the labels, but the X is unknown and requires some cost to generate. So where does reverse active learning come up? One example is speech transcription. So in speech transcription, data is typically collected by people reading sentences. And the task is to go from speech audio to a transcript. However, the data is kind of collected in a reverse way, where we have access to all the transcripts. There's certainly no lack of text text. But the expensive part is having readers read these transcripts to produce a speech audio, so we have to query this for a cost. Another example that I've worked on in the past year is sim-to-real semantic segmentation, where data is collected by rendering a 3D scene. So the task is to go from a photorealistic image of, say, an indoor scene to a segmentation mask, say, which pixels correspond to chairs, which pixels correspond to table, et cetera, to sort of understand semantically what's going on in the image. So the data, how does this convert to data pruning? Is via proxy tasks. So we can apply data pruning for a proxy task to achieve a subset S. So we get, say, a diffuse reflectance image, which is a low quality, like 90s video game style image to predict the segmentation task. And under the assumption that the most informative images for the proxy task are also informative for the target task, we only generate those images that were important for the proxy task when we have to generate the photorealistic images, which takes hours of compute. All right, so let's look at a couple of data pruning techniques, in particular machine teaching approaches, as well as using proxy models. So what is machine teaching? Well, here's a view of sort of a simplified version of classic machine teaching. So we have a learner that's going to return a hypothesis or a predictor from one of these 5 hypotheses. And we have 6 data points, perhaps from the CFAR10 data set. And H star refers to the true hypothesis. So we can think about these as the labels for the points. The machine teaching tries to find a subset of the data such that a learner can only arrive at the correct conclusion if they make no mistakes. So for instance, if we look at X4 and X6, H2 cannot be returned by the learner because the second predictor or hypothesis makes a mistake on X4. So a consistent learner, that is a learner that agrees with input with the data set, will never return H2. Likewise with H3 and H4. However, H1 is not ruled out. A consistent learner could return that. So this is not a teaching set. However, if we look at X3 and X5 and look at the patterns of where the hypotheses make mistakes, all the hypotheses are ruled out, and this is a teaching set. So one thing you might want, well, the goal of machine teaching is to find a teaching set of small size. So for instance, in this case, this would be a teaching set of size 2, which is pretty good. One thing you might notice is that we didn't actually care about the specific labels and the specific images. We just cared about where mistakes were made or errors were made. And we can actually kind of make an abstraction where we ignore most of the information and just look at the error sets of different hypotheses or predictors. So for instance, the error set of the first hypothesis, it makes errors on data points 1, 2, and 3. The second one, the error sets is points 1 through 5, etc. So there's a classic correspondence between machine teaching and Setcover, which is kind of shown in this plot, where if you look kind of vertically, we want to select a subset of points, say points 3 and 5, such that the union of the errors cover all hypotheses. So for instance, you can see that union of 4 and 6 does not include the top point, but the union of 3 and 4 does include everything. Instead, we're going to look sort of horizontally, which will actually be more, which will be easier for our setting. Where for each hypothesis, we have a set where we have to include a point to intersect each set. So for instance, to intersect H1, we need to include 1, 2, or 3. To intersect the third hypothesis error set, we have to include data points 5 or 6. So this is great, but unfortunately, this requires knowing all the hypotheses. And for modern models like deep neural networks, there's simply too many hypotheses to enumerate. So instead, there's been a breakthrough in the last few years called something called machine teaching black box learners, where the learner's hypothesis class is unknown to the teacher. And it's an iterative process where the teacher adds to a provisional teaching set, and the learner returns some consistent hypothesis from a set of hypotheses. So for instance, you have a teacher and a learner, and it's kind of this iterative process where the teacher passes a point and its correct label, H star of X. And the learner returns some hypothesis that agrees with all the examples the teacher has shown so far. So what does this look like in our other kind of diagram? Well, first the learner will return a hypothesis, and we can compute where that hypothesis makes mistakes to get the first error set. Then we can pick up first, our algorithm picks a teaching set, S1, maybe let's say just the fourth point. Then the learner returns some hypothesis or corresponding error set that is not intersected by anything in the subset. And we include the data point from S1, but also get to add one more data point to intersect E2. Then maybe the learner returns a hypothesis with corresponding error set E3. We have to include the previous points, and then we get one more to rule out or intersect E3. And this is a teaching set, sure enough. We propose in our paper black box data pruning, where it starts off, where it's similar in that there's error sets. Say the first error set comes in, and we select a subset to intersect this error set. But then there's no constraint that the subsets have to have this sort of nested structure. If you recall in the previous example, S1 had to be a subset of S2, which had to be a subset of S3, et cetera. Here we have no such requirement, which gives our algorithm more flexibility. So maybe the third error set comes in, which is not covered by S2, and our algorithm picks a subset S3, which is completely different from the S2 and S1. And sure enough, this is a teaching set. We actually got a smaller teaching set of 2 instead of 3, like it was for the black box machine teaching. So our algorithm involves keeping probabilities for each point in the data set. So pi for each point I. And it's an iterative algorithm where we, at every iteration, we sample a subset S where point I is included with probability pi. Then we train a model M on that subset S. We can compute the errors to get an error set. And we increase pi for the points where M makes a mistake, errors. And in this way, we're intuitively seeing which points the model currently makes mistakes and upweighting those points. So they're more likely to be seen in future subsets. So this rather simple, if you instantiate this algorithm with the right way of increasing pi, then actually we get some theoretical guarantees. It's NP hard to achieve minimax asymptotically smaller subset than our algorithm, which is different from existing black box machine teaching methods. So we get this added flexibility allows us to get a better theoretical guarantee and actually matches the NP hardness lower bound. Plus, we can achieve the near optimal number of learner queries. So the number of rounds that we have to select the subsets is actually near optimal. We also have experiments. So we look at 6 image classification data sets, CFAR 10, as well as 5 others. 3 model architectures. So these are all convolutional neural networks, ResNet 10, VGG, and MyrtleNet. And 7 methods, R algorithm, as well as random sampling, previous black box machine teaching methods, which we denote by the initials of the authors, DHPZ and CFLM. And the top 3 methods from a data pruning survey, in particular, forgetting which works the best among these 3. So if we look at the results when we vary data set, by the way, down and to the left is better. So we want small subsets with low test error. So in all cases, the 3 machine teaching approaches achieve the best results. And the next best method is forgetting events. We can also vary the architecture, and we find again that the machine teaching techniques are performed relatively the same across these different architectures and achieve the best results again. Whereas some of the baselines like entropy and grand actually have pretty different performance for these different architectures. So the takeaways here are that machine teaching methods provide state-of-the-art empirical data pruning results and have near optimal theoretical guarantees. And the key insight for algorithm development is iteratively focusing on including data points where errors are made. So that's all I wanted to say about the machine teaching approaches. Next, I want to talk about proxy models. So this section will be pretty short, and then I might skip ahead through future work and then we can get some questions at the end. So forgetting events, like I mentioned, something just one slide of background is a method we saw in the previous slides where while training for each data point, we keep track of the number of times the prediction for a point changes from correct to incorrect, which is called by the original paper a forgetting event. And then we choose the subset with the most forgetting events. So in other words, if we were to rank the data, where on the left we put the data points with the most forgetting events, and on the right we put the points with the least forgetting events, we can pick a threshold and pick those points that have the most forgetting events. So these are roughly the points that over the course of training an entire model, sort of the prediction changed quite a bit. It went from correct to incorrect, et cetera. So maybe something like the hard points or something. So for standard training, we have data and the size of the model, which the amount of time it takes to train this model on this data will be proportional to both these. So it's proportional to the data and also proportional to the model. For getting data pruning involves first training in order to select the data points, and then training on the selected subset. So in the first stage, we train the model to get the forgetting events. Unfortunately, this takes as long as if we just trained on everything. And then we can train on just the subset, which will take less time. But the idea of this paper can basically be summarized in one slide that we call select via proxy data pruning. And we test out and show experiments for this technique, where the selection is done with a smaller model, a model that actually achieves lower accuracy, so worse performance, but actually serves just as well for estimating the forgetting events. So in particular, it's several percentage points lower than the full model when we train on all the data. But that's all right because the points it selects are also work well for the large model. So in this case, since we use a smaller model on all the data, and then the large model, the full model on a subset of the data, we might actually get some time savings. And sure enough, for CFAR 10, we use ResNet 20 as a small model, ResNet 164 as a large model. We're able to cut about 50% of the data. Of course, we need to account for the overhead of the selection, but overall, we run about 50% faster training for the same performance. So you can swap out standard training with this sort of training and get the same performance, but in 2/3 of the time. So that covers proxy models, and it looks like we have, let's see, less than 10 minutes. So actually, I'll just very briefly run through future work. So there's a new paradigm in machine learning of this like fine pre-training paradigm, where you first pre-train on these internet scale data sets, then fine-tune on these curated data sets before deploying on domain-specific validation sets or the target task. So this naturally comes from there's a trade-off between how much data there is, data set size, and the relevance. So generally, you can find internet scale data sets that have hundreds of millions or billions of points, but most of it's not very relevant to your target task, down to a few hundred or thousands of data points that are more domain specific and very related, but there's just not many of them. And because we're changing the distribution, this inherently has a large transfer across data distribution, and a large portion of the data can be irrelevant. So I think active learning and data pruning are very promising, and initial results speak to this as well. I think I'll end it there. I'd like to acknowledge the NSF for funding my PhD, IFDS for funding my postdoc, all my collaborators who worked with me on these 6 different projects. And thank you for your attention. Are there any questions?
Thank you very much, Steve. That was a great talk. We kind of exceeded the time today. I was a 50-minute class, but there's a question in the Q&A box, and I would like to invite you to take the question. And with that, I think we're gonna wrap up today's seminar.
Okay. Let me just read the question real quick. So the question asks, one of the slides showed that by leveraging binary search concept, one can pick the data points that need to be labeled, thereby reducing labeled data size and hence computation for model building. My question is that one needs to pay the cost of ordering the data points so that one can leverage binary search. Would the cost of ordering data points always be lower than the cost of building model with all the data? Yeah, so I would answer this question by saying that we're sort of looking at 2 different applications with 2 different techniques. Active learning is for decreasing the data requirements, which just, I think is referred to as the cost of ordering the data points. And this is more the focus of that slide rather than the machine teaching data pruning, which involves lowering the computation. Thank you for the question.
All right, and with that, we're gonna end here, and we will see you next week. Thank you so much for your patience, and have a good night. Thank you, Steve.
Thank you.